there's n minus I things behind it that are larger.
So basically the weight function was designed to keep track on the stuff.
Yeah. Now it's important to note that the weight function, how it's set up, either will help you derive functional equations or make it impossible to derive something useful. So it actually really matters how that weight function is set up. Okay. So now, why is this useful? Here. So now we can use this. We can use a functional equation to compute this expression. Because we want to compute this and then extract the t to the r, the coefficient of t to the r. We can use the functional equation. In a sense, you imagine just taking this, substituting it here, and then you have a bunch of ones and some t's, and then each subsequent thing you just re-chug back into the functional equation to be able to quickly, recursively compute this polynomial. And then you can do some tricks such as if you're looking for the r is equal to 2, then you don't have to keep track of permutations with 3 or 4 or 5 occurrences. So you can cap the, if you get expressions with t to an exponent that's larger than r, you can discard things as you go along as well. And so there's different computational tricks you can apply. So the idea is that we do this. Extract the coefficient of t to the r. And the nice thing here is if you finagle some of these tricks, then this can actually be implemented also in polynomial time. One remark is you would also have a polynomial time growth into the memory you need as well as you keep track of some things, but you can create a polynomial time algorithm for computing this.
In which variables?
In n.
Okay,
Yeah.
thanks.
Okay. So now this was just to give motivation for how these weights and these functional equations work. And so this particular case is inherently interesting because there's specific generating functions known for fairly small r's, and there's already been a bit of work done for this. So instead, we can take this and we can begin extending it actually. So this general idea, we can extend it to say the pattern 1, 2, 3, 4. And the general methodology still holds. So we can get this time we'll have variables that look like t and then x1 to xn, and then we'll also have some y1 to yn. So we need another set because when we look at 1, 2, 3, 4s, we need to keep track of things that can become the 2, 3, 4, as well as things that can become the 3, 4. So we need two sets of variables to keep track of potential 1, 2 patterns as well as 1, 2, 3 patterns. But you can do the same sort of thing and derive another weight function, and then derive analogous functional equations and so on. This is much more interesting because for length 4 patterns, not much has been done. So, for example, using this methodology, we can compute, or we have computed, say the n equals 70 term when you have one occurrence. This was using Maple. And so any sort of naive approach would, at least with Maple, you might get up to maybe n is equal to 9 or 10 or something like that. So just to give you an idea what this is,
170 factorial is more than the number of molecules in any many process.
so this is something on the order of 4.335 10 to the 59. We have the exact number, of course, but this is a 60-digit number. We got some help from Manuel Cowers at Risk in Austria. So he implemented this in C, and then he has bigger and better computers than us. So he was actually able to find the first 200 terms. And so this thing is something on the order of 181. But of course we have the exact number, right? So 182-digit number. As far as I know, this methodology is the only way to compute numbers this large in this scenario, or even come close to it. Okay. Now, let me now comment.
That's what I remind me, there's no known formula for currents, you know?
No, so for this, yeah, we tried this. We tried to see if the sequence is p-recursive, but it didn't seem, as of now, we couldn't guess any sort of form for it. So, and so you can also extend this to a little bit different, but you can also extend this to say the pattern 132 and analogous patterns that are longer. It's the same sort of method. And these are not too difficult to do. Now, so for example, with the 132, the idea is that you keep track of the Q1 pattern at the end as you go along. Now, if you try to extend this to another pattern, you get issues. Right? So let's say the 213 pattern. And now, this pattern is equivalent to this pattern. So in a sense, anything you want here, you could just compute this in its equivalent. But discussing the issues here will help motivate the next step. So the idea here now is that I might have a 1-2. I would have to keep track of 1-2s at the end. Now previously, for example, in the 1-2-3 case, I can keep track of this 1-2 pattern. And it's enough for me actually to just keep track of what's the value of the 1. Because as I insert the element I at the beginning, if for the 1-2 pattern, the 1 term is sufficiently large, then I form a 1-2-3. So it's sufficient to keep track of just one item. Here you have an issue because if you try to play the same game and insert things at the beginning, actually this number has to fall within a window. So it's not enough just to keep track of where one entry is. So it matters that you have some idea where both the entries are. So you start getting complications with this. And so basically, you can extend this idea to so now you need variables in T. So now instead of x1 through xn, now I need many more variables. One to help keep track of the first term, the other to help keep track of the second. So this is for I. And then you can begin defining from here even uglier weight functions based off of these. And in the interest of time, I won't actually write it out. It's ugly, but it doesn't really motivate anything. And again, we can. Oh, sorry.
So conceptually, if you can define the weight function, so technically you answer to the question for Pn of R.
Yeah, so finding the right weight function is not necessarily a trivial task.
Yes.
And then from there, deriving the functional equation properly is not necessarily a trivial task because you don't necessarily know if the weight function you picked works until you kind of start grinding away with trying to derive a functional equation. So that's the complication here.
So things get complicated here because you're inserting things in the beginning, right? And you have to fit inside the window. But for this pattern, if you put something in at the end, then you're only able to keep track of the first part of the 2-1 pattern. Is there a reason why that doesn't work?
Correct. That does work.
Because it's equivalent
But-
to 1 for 2.
Yeah.
It's actually the
So,
same.
so that does work, but I guess in the next step I'll show why I don't want to take that shortcut. And so pretty much, so from here, for notational convenience, we can view these variables, these x variables as a matrix of variables we can define some matrix operator R1, where R1 of xn I get you some n minus 1 by n minus 1 matrix. Essentially, it deletes a row and then combines 2 columns and scales the diagonal in particular. And then with these things, then you can finally derive a functional equation for this object. And it would look something like n, and there's some stuff here, and then Pn minus 1. And this matrix operator, there's a T in here too. So you can do this and it's very ugly. And you get something much, much more complicated than you really need to compute this because this is just equivalent to the 132. Now, finally, the reason for this is that now when I shift up to the difficult pattern, I want to insert things at the beginning. Now, the things I need to keep track of, the last 3 terms are essentially a 2-1-3 pattern of a certain type. And the last 2 are a 1-2 pattern of a certain type. And so this machinery is necessary to help in this context. And pretty much just like in the prior extensions to longer patterns, we now need more variables, xij's, as well as yij's. We need an additional matrix operator. R1 and R2. And I should note that the need a wave function, and I should note that the wave function here is not, or at least for me, was very non-trivial to find. That basically the wave functions I tried just didn't work. I couldn't get a nice functional equation for a very long time. And so here I had to do something very weird, like a key to the stuff, xij, where you had, say, ABs, and A was equal to something, and B was greater than something, and YIJs, where B was equal to something, and then A was greater than equal to something, right? And so there's very weird little nuances in how the wave function is chosen to be able to derive the functional equation. And then now just to wrap up, so using this, and then also getting some help from Fredrik Johansson, also at Risk in Austria. Using this and then simplifying, so again here we're able to derive a functional equation of a certain type. Then using this, then finally we're able to crank out the 31st term for the avoiding sequence. This was something like and so this is 6 more digits than the previous record. So, you know, I think I'm out of time, so I'll wrap up here.
Time for one couple of questions.
Yeah. What's the complexity of the algorithm you get for the 1, 3, 2, 4?
Bad. Exponential-ish. I didn't do a careful analysis. But it's also highly, highly memory intensive.
I know there's certain people look into this have philosophical views as to how hard it is to calculate, you know, these terms and stuff like that. Do you have any particular views whether, we will ever if anybody knows, the 1,000th term?
Yes. So some famed individuals have claimed that not even God knows the 1,000th term of the sequence. Namely one of our organizers. I'm not sure. I don't think we'll actually be able to compute the 1,000th term. But I can't make any comments on what God does or does not know. Anything else? Okay.
These new ones, are they in the